All right, so Magnus, head up. We are pumped up and ready to go. Our phones are put away, our headphones, our whatever we got going on. We're putting everything away, and we're going to look on page 81 at problem number 12. This first section of chapter 1 is about what they call modeling. And what I don't want you to be afraid of that term, because what I want you to understand is a model, a mathematical model, is anything that represents a problem. So it can be a table, a chart, a graph, an equation, any way you have of taking the words on the page and expressing them mathematically. So the first one we're going to look at is problem number 12 on page 82 of our book. In the notes, it says, well, it says page 81, but obviously you turn the page to page 82. And we're looking at problem 12 in the book. According to the numerical model, what has been the trend in males joining the workforce since 1954? Now, don't stress. Look up at the chart. What can you tell me about the male numbers? Males joining the workforce. What can you tell me?
It's more.
What's going on? What's the trend?
Oh, it's decreasing.
It's decreasing. Would you agree? Yeah, it's decreasing. In what 5-year interval did the percentage of men who were employed change the most? So you said they're going down. They are actually all going down. When did it decrease the most? What 5-year period?
70. Oh, is it 1999 to 2004?
Let's see. 69 to 74. How much did that go down? 3.2. I'm doing the subtraction in my head. I think that's right. What about 79 to 84? 3.3. So I'm going to say 79 to 84. What about you? Does that seem right?
What about 1999 to 2004?
99 to 2004 is only 3.1. I mean, no, 2.1. Oh, 2.1. All right, well, that's easy enough. What about number 20? Oh, today's Dr. Greer's birthday. So pretend you're going to buy him a birthday cake, and you walk into the bakery, and we can get a 9x13 cake. It is Dr. Greer's birthday. Or we can get a 8-inch round cake. All right. And your question is, which option gives the most cake for the money? How are we going to figure this out? Well, it says it costs the same amount. So money isn't really the issue here, because you're going to go in and you're going to pay, I don't know, $10 for that cake and $10 for that cake. So we just want to know which one's the biggest or the best deal. What? You want to find which one's bigger, right? Which means we'll want to find what? Volume? We'll want to find volume, right? Now, what do we know about how thick these cakes are? They didn't tell us how thick they are, did they? Or what did they say about thickness? Okay, does anyone have a book?
Page are we on?
It's really hard to read when you don't have the book. Alright, so here's the deal. It says, a bakery sells a 9 by 13 cake for the same price as an 8-inch diameter round cake. If the round cake is twice the height of the regular cake. So this is like a layer cake. This is twice as tall as this one. This is your regular, just rectangular cake. Now, they don't tell me how tall either one of them is. They just say this one is twice as tall. So let's suppose this cake is 1 inch thick. Then this one would be 2 inches thick, right? So let's just do that. So here we go. What is the volume of this rectangular cake? 9 times 13 times 1. Length times width times height. So what is that? 117? Oh, cubic inches, sorry. Cubic inches. So you go in and you buy Dr. Greer this cake, he will be getting 117 cubic inches for that cake, if I multiplied right. All right, now what about this one? This is your round layer cake.
You define the height.
So the height's 2.
Alright.
How do we find the volume? What shape is a round layer cake? Cylinder. It's a cylinder. It's like a tube, right? So anybody, someone impress me. Who knows the volume for a cylinder? It's close. Pi r squared h. R stands for the radius and h stands for the height. Now you don't have a book. This was an 8-inch round cake and it said the diameter was 8. So the radius is going to be 4. So our volume is pi times 16 times 2, or 32 pi. That's the volume. So let's get a decimal for that so we can compare, because we're trying to decide which cake's bigger. Alright, so Jalen, save you the trouble, you said it's 100.48?
Yeah.
And that's cubic inches. So you go into the store, you know you're going to spend $10 on a cake. Should you buy Dr. Greer this one, or should you buy Dr. Greer this one? The top one, because you get a little bit more cake for your money, right? Same price, so you want, like Jalen said, you want to buy the one that's bigger. This is the bigger cake. Now, who is troubled by this assumption that I made? Is anybody troubled by that? Because remember, they didn't tell me how thick they were. They just said this one was twice that one. So I said, okay, let's just let that one be 1 and that one be 2.
You just make up the number.
Do you think it's going to matter in the answer? Now remember, what was the question? Which one has more cake, right?
Yeah.
Do you think it's going to matter if I made this a 2 and this a 4?
No.
Do you think that would still be bigger than this one?
No.
Yes, it would be.
Yeah.
Because essentially all you're doing is doubling that and doubling that. That one's always going to be bigger. So you said, can I just make up a number? And the answer is yes, I can. Yes, I can. Because all I want to do is compare these two, size-wise. All right. Well, that was fun. Let's try turn the page. Now we're going to solve another equation.
Are we still in the book?
Nope, we're on our notes. We've been in our notes, but our notes referred us to the book. Now our notes are just have some problems on them. All right, so what do you think? You had a question like this on your test, kind of. What do you want to do with that? Well, I wouldn't try, God bless you, you can try to factor that, but I sure wouldn't with that fraction in there. Could you use a quadratic formula?
Yeah.
Yes. Now, you're sitting there with a calculator, so does it really matter that there's a fraction in it? No. But could we get rid of the fraction before we did the quadratic formula?
Yeah.
Yes, and how would we do that? Multiply by 3. So we'd have 3x squared minus 12x minus 1 equals 0.
Yeah.
Now, it isn't gonna make a bit of difference, kids. If you don't mind the fraction, then go ahead and solve it like this. Personally, I'd rather not do the fraction. I'd rather get rid of it. Caitlin? What's 0 times 3? That's the beauty of 0. You can multiply by anything and it doesn't change. So, x equals negative b plus or minus the square root of b squared minus 4ac. Oh, by the way, somebody missed the quadratic formula on the test. No partial credit. We gotta get it right. Negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. Watch it there in the middle. Again, we have a double negative. So I'm going to add, I think that's 156. Don't even think about canceling these. If you do think of that, block it out of your mind. You can't cancel those. We need to simplify that first. So 156. I don't know, what is that? 2 times 78. 78 is 2 times 39. 39 is 3 times 13. I think that's it.
Yeah, so 239.
So 12 plus or minus 2 times the square root of 39 over 6. Now I can cancel, right? I'm hearing that from lots of people. Now I can cancel. I have a 12, a 2, and a 6. So I'll pull a 2 out, and I have 6 plus or minus the square root of 39.
Good morning, this is a reminder that all sophomores should report to the auditorium for a meeting during flex. All sophomores report to the auditorium. I need Mario McCullough to the front office and Emma Whitlock.
All right, I guess we're done. So Emma, you can leave it here and come back and get it, or you can take a leave. Put your calculator away if you're gonna leave it. All right, so now we have flex, folks. Good job. Yep.